Hello and welcome to this video about linear transformation proofs. In this video we'll prove that these particular sets are subspaces of these vector spaces. So here are some quick definitions of what things are. This is what a kernel is. It's the set of all vectors in the domain that the linear transformation maps to zero. It can range from only the zero vector to being the whole domain. It is also called the null space. And this is what the image is. It's the set of all vectors that the linear transformation maps all of the vectors in the domain onto. It's all of the possible output vectors that this function can produce. It's also known as the range or the column space. So now to prove this statement, that the kernel of L is a subspace of the domain V. That is, it's not only a subset of V, but it's a vector space itself. So now to prove this. The kernel contains at least the zero vector, because it maps it onto zero. We got this from theorem 3.1 part A. So the kernel of L contains at least one element, so it isn't empty. So we'll use this past theorem to show that it's a subspace of the domain V. We know that it's a subset of V because it can form some of the input of L. So we only need to show that it's a vector space. And we can use this theorem to show that it's a vector space much more quickly. This theorem requires us to show only two things. Firstly, that the sum of two vectors that are contained in the kernel is itself contained in the kernel, and that a vector contained in the kernel that's multiplied by a scalar is also contained in the kernel. And to show that these vectors are in the kernel, it's only necessary to show that applying the function L to them gives us the zero vector. So now to prove these two things for part A, we'll suppose that these two vectors are in the kernel of L. So now we'll apply the linear transformation L to the sum of these two vectors, and we can split them up into the sum of two of these functions, because it is a property that they have. And because these two vectors are in the kernel, then after we apply the function L to them, L will return 0 for each of them. And the sum of two zeros is 0. It's a property of one of the zeros that it will disappear, leaving the other zero behind. So the linear transformation L applied to the sum of these two vectors maps it to 0. So the sum of these two vectors is in the kernel. And now we have to apply L to a vector in the kernel multiplied by a scalar. And we can easily take the scalar outside the function like this, which gives us a scalar times the zero vector using the property of kernels. And we can use a past theorem to give us the zero vector as an answer. And so we've done it. A scalar times a vector in the kernel is also in the kernel. So after combining these two results together, we can say that the kernel of a linear transformation L is a subspace of the domain V. Now to prove the next part of this theorem, which is part B. It says that the image of a linear transformation is a subspace of the codomain W, which it's mapped onto. So the image of a linear transformation is non-empty, because when we apply the linear transformation onto the zero vector, according to a past theorem, theorem 3.1 part A, it maps at least one vector onto the zero vector, so the zero vector is in the image. We'll use theorem 2.6 again to prove that the image of L is a subspace of the codomain W, similarly to how we did it before, in part A. So we only need to prove two things to show that it's a subspace. Firstly, the sum of two vectors in the image must also be in the image. And the product of a scalar and a vector that's in the image of L must also be in the image of L. The image of L is obviously a subset of W, because the image is mapped onto W. So now to start our proof. Supposing that these two vectors u and v are in the image of L, then there must be vectors x and y, such that applying the linear transformation L to them gives us u and v, because u and v are in the image of L. So we know that these vectors are in the image of L, because it's L applied to vectors in the domain of L. So applying L to the sum of x and y must also be in the image of L. We can split them up into the sum of these two functions because it's a property of linear transformations. Applying L to these vectors gives us the sum of u and v. And so the sum of these two vectors is in the image of L, because it's equal to L applied to x plus y, which is in the image. So then applying L to a times x is in the image. We can take the scalar outside the function because it's a property of linear transformations. We can then evaluate Lx to give us u, so that we finally end up with a times u. And this is in the image of L because it's equal to L applied to a times x, which is in the image of L. So we've proven both things that we were required to prove, so that the image is a subspace of the codomain W. So we've proven both parts A and B, so we've proven the whole theorem. I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful and interesting in the comments. Feel free to share this video, and thanks a lot for watching.